So moving forward, looking at Chapter 4, we're going to look at the basis of statistical testing. Why do we actually test the statistics that we have derived from our study? So an overview of what we're going to be talking about. We're going to be talking about sampling, different samples and populations, errors associated with sampling. We're going to talk a little bit about null hypothesis. And with the null hypothesis, learning about the hypothesis and learning about the null hypothesis can be a little bit confusing, but it's a very important area that you really have to have a good grasp on whenever you're reading any sort of journals or any studies that you come across. We're also going to be looking at statistical significance. And basically what statistical significance is we're going to be looking at once we gather our data and once we run our data, whichever program that we possibly would use, what is significant? And that's another very important area when you're reading research or when you're reading journal articles of somebody who has completed a research project. And the reason why significance in having a good understanding of it is so important is because you can read a journal article and they have their hypothesis, they come up with their end result, whether they accepted the hypothesis or not. And they can say that it's statistically significant, but once you look at the numbers, you'll have a better understanding of, is it really statistically significant? When we really look at the statistics, is there a significance in group 1 versus group 2? The other thing, we're just going to briefly go over normal distribution again because we did go over it in Chapter 3, but we'll go back over it a little bit. We're going to talk about powers, just a tiny bit touching on powers, the power of basically what our results are, and our confidence intervals. And basically a confidence interval is exactly what it says is, are we confident in the results and in our conclusion of the research that either we're reading or if we had actually done a research project ourselves? Some general terminology that you will read when you're assessing different research projects and journal articles is they'll talk about a population. And basically a population, the definition from our book says that it refers to all people or items with a particular characteristic of interest. So the description in the book, they talk about all people with cholera or all people with a hearing impairment waiting for a hearing aid. We, in dental hygiene, we could say all people that have periodontal disease. That's a population. That's a whole group of individuals with a similar characteristic. A sample refers to a selection of that group of people. So out of that whole entire group of cholera, we maybe there might be 1,000 people, but we might only sample 100 of them when we're testing. Same thing with hearing impairment. You might only sample 40 people out of 500 people. So, and then the sampling is done through a process as well to make sure that, once again, that there's no errors and that there isn't any outside external validity issues with how you selected that particular group of people from that population. A couple more definitions, terms that you should be familiar with whenever you're reading research or reading any sort of journal articles. You might want to have a little bit better understanding of what statistics actually are. And basically, statistics are something that are used to calculate various rates from raw numbers. So when we talk about rates, which are typically used, you'll see rates typically used a lot in public health. which basically is where my bachelor's degree was in. You're gonna be looking at numbers, looking at various research that's out there, and once you have those numbers, we're going to look at how often are we seeing the same pattern. So if we're studying something in particular, we're going to look at the rate, like what is the rate that these individuals are acquiring cholera. The rate is more or less how often that you're going to be seeing something occur. And statistics are basically used to analyze many situations important to public health, such as risks, benefits, costs, which must be balanced against each other when decisions are made. And the only reason I throw this in about public health is because it's very easy for me to identify public health with healthcare. So when you're doing a study, or you're reading a study and you're looking at the statistics, a lot of times when they come up with an individual plan, or they come up with decisions about how they're going to continue on, they have to look at what are the risks to the individuals, what benefits would it be to the individuals, and what is it going to cost. And so using this in a public health form and using this in a healthcare form, it would be comparable to, are we going to do a test on an individual, an experimental study on an individual? What are the risks going to be for that individual? And once again, we've all heard of clinical trials. What would the risk be for that individual? What are the benefits going to be? What are the costs going to be? Is that going to outweigh what benefit the individual is going to have? And when we look at it on a public health, just kind of throwing this out there, when you look at it on a public health level, what they're looking at is possibly starting, maybe there's a program, maybe there's an asthma program, or like I initially talked about early on in chapter 1, a tobacco cessation program. What are the risks going to be for this program? What are the benefits going to be, and how much is it going to cost? So those things are all taken into consideration, and generally speaking, where I'm going with all this is you have to have the statistics in order to back up what you're going to do. So you have to have those numbers that are identifying that there is a problem, or identifying that there is a correlation. Those numbers come from statistics. And just another thing that I throw out there all the time is that whenever you see N, it's always going to be consistent with the number. So the number that we're dealing with, like a population of 300, it may say N is equal to 300, and that means that's the number of individuals usually that they're working with in that particular study. So looking at the difference between samples and population, why do we use samples versus using whole populations? It's really kind of simplistic, that it's cheaper, not having whole groups, whole huge populations, and just taking a little sample of the individuals that have something in common is going to be cheaper. It's going to be way quicker, obviously, to test 40 people versus testing 500 people. And also it's easier to recruit a smaller group of a sample of individuals versus a whole population. So as I mentioned earlier when I was talking about how we gather our sample from the different populations, we have a couple different terms. Once again, something that's pretty important that you have a grasp on or have some knowledge of is something called simple random sampling. And simple random sampling is exactly what it says. It's just random. We're just going to, you might have a sample of individuals from a population, and you might have them count down 1, 2, 3, 4, and 1, 2, 3, 4, and you might take every second person or every fourth person, and that's just basically what random sampling is. Cluster sampling is something that you have a larger group, and you go into that large group and you take just a small sample of individuals from that group. And the book talks a little bit about going into England or the UK and going into one of their boroughs, and within that borough taking just a group of people, just a cluster of them. That's pretty much what cluster sampling is. Opportunity sampling is basically the opportunity's there, so we're going to sample this particular group of people. Dr. Sal Sanders wrote a study a few years back on individuals and why they exercise at our local park. We have a big local park here called Mill Creek Park, and they have a walking trail. And he set up a little table, and he had just a very random questionnaire, and he would just stop people as they were coming to the end of the walking trail and ask them questions. And so that's basically an opportunity sampling. The individuals that you want to sample are there. Now, he could have set up there on a very snowy, cold day and probably would not have had the same pool of people as he would if he had set up on a beautiful spring day or a beautiful fall day. So that's basically what our opportunity sampling is. And then something called snowball sampling is basically when you have found somebody that you want to identify with. It's usually used for qualitative analysis versus quantitative analysis. Quantitative meaning numbers. Qualitative is more of you're going to see snowball sampling as more of a one-on-one type of an interview. So you may be interviewing individuals. I always use the example of prior inmates that have been incarcerated, are now out of prison, and you maybe ideally wanted to do some sort of a study as to have they, if they return to the same type of behavior that got them into prison in the first place. So you would identify with that first person that was in prison and have them possibly refer you to somebody else that has been in prison as well. So it's kind of a snowball effect. You get one person, then that person adds to another, to another, to another. And then volunteer sampling is really just what it says. You hear on the radio from time to time that they want volunteers to be in an acne study or a weight loss study. Those individuals volunteer to be sampled. They volunteer to basically be the specimen for that study. Very important area to look at is something called sampling error. And a sampling error is, even though we're selecting samples from a population with what we like to think have general characteristics that are the same, we may end up with differences between the samples and the populations. And one way to look at that is if we were doing a study and we took a whole population of, say, 400 people, and we wanted to find the mean of those individuals. If we took that group, that population, and we did the mean on them, we took a mean on them, and then we took a small sample of that population and did the mean on them, the means should be very similar. But if we do the mean on this population and then on the sample, and they're not very similar, then we have a sampling error somewhere along the line. something has gone wrong with this particular sample that we have organized for our study. Because of the sampling error, we might expect random differences between two samples in the population. So what we're saying is, going back to the example that we just talked about with cluster sampling, if you go into, say, the borough of England and you take a cluster of individuals from that borough, you could look at the whole borough as a whole, and you might have half of those individuals in that borough being very wealthy and the other half being very poor. But maybe where you gathered your information, or depending on what your study was, you only took individuals that were very poor. And so that may have a huge reflection on what your study actually is, versus had you taken individuals, same amount of individuals from the rich group versus the poor group. That would make it very reliable and very valid, valid being the key term there. But like I said, if you have sampled and the samples aren't normal or they aren't equal, then you're going to come up with a sample error. Once you have a sample error, very difficult. You have to go back in again and start looking at what you've done wrong, and or the study that you've read, where they went wrong in that study and how it can be corrected. Probabilities, when we talk about probabilities, it's pretty much what it sounds like. What are the chances that this is going to occur? What are the chances? It's the actual likelihood that the event that you're studying is actually going to occur. So we're looking at more chance, and how probabilities are calculated or figured out is very simple. We talk about the target and divided by the number of possible outcomes. So this example, which I really am not crazy about, is there's two sides to a piece of bread. So that's going to be the number of possible outcomes. And we're talking about one side of toast that's buttered versus having two sides of the toast all together. So the probabilities, it's actually a division. So one side of toast divided by two sides to a piece of bread, and you end up with your result. Now, the book talks about a couple different easy to figure out probabilities. On page 135, the probability of selecting a club from a pack of cards. So a club suit, there are 13 clubs in a pack of cards, and you have 52 cards. So 13 divided by 52 is going to give us 0.25. So a quarter, basically. So you have a 0.25 chance that, or 25% chance that you're gonna come up with a club out of a pack of cards. They also talk about the last example, probability of rolling an even number on a dice, and you know that there's 6 sides to a dice and there's 3 even numbers on a dice. So 3 divided by the total is going to give us 0.5 or 50%. Now, the range of probabilities that you can look at, and once again, I go back to this again. I don't want you to think that we're going to be calculating different statistics, but I want you to have an understanding when you read something, that you're going to have that understanding of whether or not this is significant. So the probability, when they put a probability in a study, The range is going to be from 0 to 1. You're always going to see anywhere from 0 to 1 is going to be the range of the probability. 0 means just that, 0. The event is not going to occur. So if you end up with a 0% on your probability, then the event's not going to occur. However, if you end up with a 1, which is, whole 1, the event is probably definitely going to occur because that's 100%. So we are 100% sure that that's going to occur. So when we look back on our example in the book of the probability of selecting a club from a pack of cards, we did the 13 divided by 52. We ended up with 25%. So 0.25, that's probably not the best probability, but it's still somewhat of a probability. So you're never going to see the range ever be anything more than 1, obviously, because we're dividing one number into itself. So it's always going to be occur between 0 and 1. Like I said, 1 meaning nothing's going to happen, and 100% if we had something divided by, say, 13 divided by 13, we're going to end up with 1. That means, yeah, it's definitely going to happen, 100%. So scenario 1, looking at sampling errors, identified on page 133. Like I said before, it's really kind of hard to identify where the error came in at, where our sampling error came in at. So this just shows a little scenario. Population mean from the group 1 is equal to the population mean in group 2. Then we've had a sampling error. We're not quite sure where, but we've had a sampling error. Then we have sample mean 1 is less than sample mean 2. The difference here did not come from the population mean, from the group itself, as we talked about earlier. It came from our sampling, how we sampled those individuals. There was an error in it. Going back to using that example once again of using the really poor people in your particular study is probably going to make a difference in the overall study. Even using the example when I used to teach dental public health, I used to talk about oral hygiene. And when you study individuals with oral hygiene, chances are you're going to see individuals that are very rich, or not even saying very rich, but a little bit more well-to-do versus the very poor individuals. The very wealthy individuals are going to have much better hygiene. And that's just basically because they're going to have the money to have the resources to purchase what they need for good oral hygiene, meaning toothbrush, mouth rinse, floss, versus the poor individuals that aren't going to have the money. So that's really not going to be an absolute unbiased sampling of individuals. So that's what we're saying with this scenario, is that our population was equal, but there was a sampling error along the line, and that's going to end up coming in and skewing or upsetting the balance between sample mean 1 and sample mean 2. But that difference came from the sampling error, not from the population itself. Now, scenario 2 talks about the difference between samples due to the real difference in the population. Once again, going back to my example of the individuals from the poor group and the individuals from the rich group. That is where the actual error occurred, in the population itself. Not what you sampled out of it, but the population itself. So once again, if we went in to a if we went into a borough in the UK or England, and we took our sample from the rich and the poor, that's where our problem came from, right there in the very beginning, the population, which is going to trail down to having an actual sample error because we didn't sample the correct group of people. And so just looking at this, we're saying population mean 1 is less than population mean 2. That's our error right there. They're not equal starting out. Brings us down, we've got a sampling error going on, and then we're going to look and we're going to see that sample mean 1 is less than sample mean 2. Same result as we saw in scenario 1, sample mean 1 less than sample mean 2, but the difference has to do with the real population, the group that we actually started with, not how we picked the individuals to sample with. So not our sample, but our actual population. Very hard to determine that. Sometimes you go into a study and you think you have everything kind of figured out, and once we come roll down the hill and we get to where we're supposed to be, we see this big difference. But we have to figure out where it came about. Did it come about in our sampling, or did it come about in the actual population that we identified with? So moving forward a little bit, talking about once we have our population, once we have our sample of our population, we're going to do some tests. And what we're looking for is to see how significant the results are that we have come up with. So we call that tests of significance. Or is there a significant difference between, once again, if we tested the very rich and we tested the very poor on their oral hygiene, we come up with our numbers. We have to test those numbers to see if they're significant, if their reliability and validity is going to be something that we can use to actually state that we have a confidence level. So there's two types of test of significance. One is parametric and one is non-parametric. Parametric, you know a little bit about the data. One must estimate at least one of the population parameters from the sample. Always assume there's a normal distribution. Parametric tests of significance are always used for interval ratio scales, which we talked about early on. Interval ratio scales, meaning they're continuous. They're not categorical. Now, non-parametric, we know nothing, which to me makes complete sense because you're assuming everything. With nominal and ordinal level, remember we said that's categorical. We're looking at categories. We're not looking at it being continuous. It's not nearly as reliable as what you're going to see with parametric tests of significance. So looking at our tests of statistical significance, looking at testing non-parametric, one test that's used quite frequently and a lot of people are familiar with it, and I remember when I had my first, I believe, undergraduate statistics class, and we had to actually do a chi-squared, like fill out the whole contingency table and put our numbers in it and actually do the calculations. Now we have computer programs, primarily being SPSS, which the book talks a lot about, but like I said, we are not going into we're not actually going into doing the testing. We just want to be able to be better consumers and be able to understand the statistics that we're reading when we are reading research or reading journal articles. So chi-squared, usually used with categorical data, which we know is nominal ordinal. It compares a number in a group with the actual number. Okay, the expected number can be based on theory, experimental, comparison groups, but we kind of have to simulate a number. We have to make up a number that we're going to compare our number to. We have to categorize the data before we use it. It's very popular in the analysis of research data, especially survey data. Okay, so remember we've got this number that we actually have, and we could just throw out a random number we want to compare it to, or we could base it on literature that we've already read and pull a number out to compare it to. But basically, you know nothing about um, one of the areas. And it's used a lot of time to find a relationship between survey items. And once again, I said usually will be used to show the association between categorical, not continuous variables. And it's always put on a contingency table, which is a table with a lot of little squares on it. So just kind of keep that in your head. Non-parametric, it's going to be chi-squared, nominal, ordinal data. So tests of statistical significance using parametric testing, there's a couple different types of tests that are used. Once again, I do not want you to think that we're going to be actually doing these tests. What I want you to grasp from this is that if you're reading a study or you're reading a journal article and you see that the individual is using using an ANOVA. Let's go to an ANOVA, which is used only on parametric, that's used for parametric testing. But knowing that the individual is using, say, nominal ordinal data, well, we know that parametric testing is only used for interval ratio continuous. So say they used an ANOVA, but their data that they have acquired that they're testing is male female. Well, you can't use you can't use categorical or nominal ordinal data with parametric tests of statistical significance. So you would know right off the bat that that would be wrong. So there's not going to be a whole lot of weight shown into that study. So how you actually study, how you actually test the results of your study is very important. So if someone say they're going to use the chi-squared, which we know is a non-parametric testing, and non-parametric testing is used specifically for ordinal nominal data, but say they're using continuous. They're using continuous data and they're trying to put it into a chi-squared testing. It's not right. So that's what I want you to grasp out of it is what type of data are we looking at and how we can apply that data to the different methods of testing. So parametric testing, we have the ANOVA, and basically what it's going to be looking at is two or more matched groups. So two or more matched groups with lots of similarities. Another area is a t-test, and there's also something, it's also can be called a non-paired t-test or a student t-test, and it looks at the mean of two different groups. It compares the difference between the two means. Okay, so remember we talked about sampling errors and how we can see sometimes we get down to this point where we've got our population and we've come down to our sampling and we compare the means, and our population mean is normal. It should drop down to our group means or our sample means being very similar. And if they're not, then we know we have a sampling error. So a t-test is used for the comparison of two groups when the variable of interest obviously is continuous. Okay? Always assume with the t-test that the distribution of that group is going to be normal distribution. So continuing on with our tests of statistical significance, looking at non-parametric, still talking about non-parametric. One thing that we always look at is a null hypothesis. And basically what our null hypothesis is saying is that there is no difference between what you're looking at. So if we if we come up with our hypothesis and we end up having to adopt the null hypothesis, that means that there was no difference in our study. So if once again we're looking at rich and poor in their oral hygiene, and we're going to say, as our hypothesis, we're going to start out and say, through this study, I'm going to determine that there's a great difference between rich and poor in their oral hygiene. That would be your hypothesis. But say at the very end, you don't find a difference. There is no difference between the rich and the poor. Then you're going to, basically what they state is we're going to adopt the null hypothesis, meaning you weren't right. So you weren't right with what your hypothesis was. So there really isn't any difference. And so when I have on this slide, you're going to prove that not right. Basically, what you're saying is you want to see the difference. You want there to be a difference in order for that to be statistically significant. You need to have a difference. And something that we'll also see a lot in our journal studies and different research, and when I've taken about five classes, I want to say, in my doctorate program on statistics, and the one class the instructor made this a very, very big deal about p-values, and actually we had to take competencies once we were through with our coursework to make sure that we were competent in what we had learned, and each instructor gave us questions, and the one question she gave us is to explain the difference in p-values. And a p-value, it's usually used to represent the final answer when you're calculating the statistical test of the hypothesis. So looking at, if you go all the way down to the very end of whatever study you look at, you're always going to see a p-value, and that's the probability value. Because remember, going back to the beginning of this chapter, we talked about calculating the probability that something's going to happen. And so when it's significant, then we know that there is a probability that that is occurring, whatever we're studying is occurring because of one of the variables. It isn't by chance. It's for real. It is happening for a reason. So the one thing that this instructor always, or this professor always went on and on and on about is, with a p-value, even though you come up with your p-value, it really doesn't prove anything. You never want to say that it proves that our study, if we're looking at, once again, the hygiene with rich and poor, and we come up with statistical significance to support our hypothesis that yes, the rich have better hygiene than the poor, that still doesn't really prove it. It shows nothing but statistical significance. I really want to put that in your head. So when we talk about the p-values being greater than or less than 0.05, you're never going to see a p-value greater or lesser than 0.05. But when we talk about that, it doesn't prove. There's really never any proof in statistics. It shows support of statistical significance. So continuing on a little bit more on our p-values and identifying statistical significance. I'm having a really hard time saying that for some reason. Trying to identify whether something is statistically significant or not. There's some criteria that's basically set aside, like I said in the previous slide, we're always going to be looking at 0.05. That's our key number. Now, if our calculated p-value is less than the criteria that we set for significance, then we reject the null hypothesis. Remember, null hypothesis means that they're classified as statistically significant. Okay, so we reject it. We don't accept it. Rejecting the null hypothesis is going to mean that we actually accepted our real hypothesis. I know it sounds confusing, and I know whenever I would teach this in dental public health, the students would be like, huh? Why don't we just say we accept our hypothesis? It's not identified that way in statistics for whatever reason. That's one of the reasons we want to make things very confusing for you, is to say, if we have a p-value of less than 0.05, then we're going to reject the null hypothesis, which means that it is statistically significant because we are going to accept our actual hypothesis. Reverse the role here. If our p-value is actually greater than the criteria that we set for statistical significance, we retain the null hypothesis. We accept that null hypothesis. And once again, accepting the null hypothesis means there is no statistical significance, non-significant, okay? Which means then we actually reject our hypothesis, which was we were stating that there is going to be significance between the rich and the poor with their oral hygiene. So p-value, again, just a rule of thumb. If the p-value is less than or equal to 0.05, you're going to reject the null hypothesis. There's no difference. And if the p-value is greater than 0.05, you accept it, meaning there's no statistical significance. And the book goes into normal distribution. Again, we discussed normal distribution early on this semester. And once again, when we look at normal distribution, we want to make sure that it's bell-shaped. It's symmetrical in the very peak of the middle, and the tails are equal usually on each side, and that's what we're looking at with normal distribution. And remember how we identified the mean would be right down the middle of that bump, and then we would have all our samples and all our data would be clustered around that mean. And then on the tails of both sides, we probably have a few areas of data of our sample that we may have scattered out there, but those are more outliers. We discussed that already, where we would like to see everything right down the middle around the mean. That's a normal distribution. So identifying skewness, a lot of times you'll hear individuals talk about that the data was skewed, and basically what we're trying to get across with skewed data is that not all our data is going to have a normal distribution. We're not going to see everything completely centered around the mean, and we're not going to see a great deal of, I'm sorry, not a great deal, just a few of our data along the bottom, along the tail. We're not going to see that perfect normal distribution, and that's called skewness. So if we look at these two graphs, just looking at these right off the bat, I would say that whatever data we're studying here is continuous, because remember, other than the couple outliers there, it's all connected. All our graphs are distributed throughout the graphs. They're touching. So remember, whenever we pictorially display our data, if it's categorical, meaning the categories, it's going to be separated, the bars, and if it's together, then it's going to be continuous data. So just looking at this, you can see they're saying that the mean is 12.52. So the first graph, go along the bottom, and you can see the tallest peak there is probably 12.52, 12 and a half. Okay, but then look at where our data is around it. Okay, so it's not, we're not seeing this nice little bell-shaped curve. If we look at the second one, we see where our mean is at 16.86, which is almost 17. Once again, not a normal bell curve. Our data can be skewed or irregular to the negative, which would be obviously on the left side of the mean, because the mean is in the middle, or it could be positive. It could be on the right side of the mean. So both of these graphs are just showing you how something can be skewed, and meaning, once again, that there's something not normal about the data that we have collected here. So another type of distribution that you may see when you're looking again at data that is pictorially identified or displayed is something called bimodal distribution, and it's basically what you would think being the mode. And looking at this graph again as a histogram, and I'm looking and I'm seeing everything connected, so I'm sure whatever data we're going to be looking at is a continuous type of data. And if we look at the mean being 23.49, you follow it down 23 right in between the 20 and 25. Look where our mean is at. Okay, and then look at our two peaks that we have. And remember, our mode is the most frequent data, the most frequently seen data within our sample. So remember, if we had a sample of 2, 3, 3, 3, 4, 5, the mode's going to be the 3 because it's most frequently identified. So looking at this graph, we have two modes, so we have a lot of information. Just by looking at this, we see that we have a great deal of data that's very similar. Okay, it's occurring quite frequently, so hence we have two modes, and obviously it's not a normal distribution, so we don't see the bell curve, and we see that our mean is very low with the frequency at about 7. Okay, but then we're looking at frequency on this bimodal distribution. We see quite frequent distribution, almost up to 25. So it's kind of interesting how this histogram identifies bimodal. And once again, we already looked at our normal distribution, standard normal distribution with 0 in the middle, and we always kind of want it to go within 3 points, 3 levels to the right or to the left. We don't need to review that again. I think you probably have a pretty good grasp on that. And once again, the book talks about standard deviation and what the percentage is of scores falling within 1, scores falling within 2, and scores falling within 3. So this is really pretty much a review from what we had already looked at. I kind of like to bring that normal distribution and standard deviation in early on, so you have a better understanding once we're moving forward as to what it means. So type 1 and type 2 errors, we talked about this already. You reject the null hypothesis when it's true, and that's signified basically as an alpha. And type 2 errors, you reject the null hypothesis when it's false, and that's signified as a beta, the B. But really how I want you to understand it is how we talked about it earlier, is that if you have your looking at your 0.05 and looking at statistical significance, that's how you really want to identify whether or not we have statistical significance using our null hypothesis. So looking at the graph that is identified in our textbook, just kind of showing us a little bit about our type 1 and our type 2 errors. If you look at the graph, or if you look at the blocks on the left, we have no effect in the population. So on the very left, you decide to reject the null hypothesis, meaning that you have decided that there is statistical significance. You've made a type 1 error on that hypothesis. Looking at the same first display and looking at the right of that display, we're once again starting at the top. There's no effect in the population. So you decide to retain the null hypothesis. This is correct. You've made the correct decision, because if there's no effect, remember, if there's no statistical significance, you're going to retain that null hypothesis. You're going to agree with that null hypothesis, and you are going to accept it. Okay. Now, looking at the pictures on the right, you're going to say if there is an effect in the population, there really is an effect, and you decide to reject the null hypothesis, okay, meaning you're saying, yes, there is a difference, then you've made the right decision. But if you decide to keep the null hypothesis, meaning there is no difference, you've made a mistake. You've made type number 2 error, which you're saying that there is not an effect in the population. And the last thing we're going to look at is confidence intervals. And confidence intervals are present how we look at the estimate of our population mean, how confident we are that the mean falls within two particular numbers. It indicates the interval which we are all confident that the population mean will fall. It's usually centered around the sample mean, and the book does have something called an error bar graph that you can show that in a picture form. Basically, on page 155, they have a little diagram there that'll show you that they're looking at they're 100% confident that the population mean will fall within 0 and 28, and it just shows you the sample mean is at 11.90, and it just kind of shows you how it falls between 0 and 28. What we're looking at is how confident we are with our results that that's where our data is going to fall. So just to summarize what we kind of talked about already, we looked at samples, populations, how to acquire samples, how we sample people, how we sample individuals, errors that can happen when we're sampling. We looked at null hypothesis testing, we looked at hypothesis testing, tests of statistical significance. We looked at, once again, we reviewed normal distribution. We did not discuss power. I didn't really think it was relevant, and I think it's going to end up a little bit more information than what we need to know for this particular course. And we looked at how confident we are that particular numbers are going to fall within, our numbers are going to fall between two, our mean numbers are going to fall within two numbers.